You know, deep down, physics has this kind of secret language. It's a quirk in how the equations are written that can be, honestly, a little confusing. But it also points to a much deeper, more elegant reality. Today, we're going to pull back the curtain on this hidden language and see how redefining a couple of the most fundamental constants in the universe could totally change how we see the world.
Okay, so let's jump right into the puzzle. Physics has these two different ideas, spatial frequency and wave vector. Now, if you look at them on paper, they seem to share the exact same unit, reciprocal meters. But here's the thing, they're not the same, not at all. One is actually measuring cycles per meter, and the other is measuring radians per meter. It's kind of like having two different currencies that look identical until you try to spend them. And the craziest part? A lot of the time, physics just leaves that crucial little detail out. It's hidden.
And what's really wild is that this isn't some sloppy mistake. It's actually a feature of how physics is written. It's almost like scientists in different fields are just supposed to know from the context whether they're talking about cycles or radians. These dimensionless units, as they're called, are part of this hidden language. It's like an unwritten set of rules you're just expected to pick up to be in the club. And that right there is the core problem we're digging into, this hidden language of physics. It's a system that's built on these unspoken assumptions. And sure, it might work okay for the experts who are already in on the secret, but for everybody else, it can be a massive barrier. And look, this ambiguity isn't just some small thing that trips up students. It's got a much bigger impact. It doesn't just make physics harder to get into, it actually hides the beautiful, intuitive meaning that's right there, inside the equations that describe our world. But here's the really cool part. There was a recent, huge change in how we define our fundamental units, the International System of Units, or SI. And this change has given us a golden opportunity. It's a real chance to finally bring some much-needed clarity to this hidden language. And it all comes down to two of the most famous constants out there. First, you've got Avogadro's number. We all remember that one from school. It's the go-to for counting just enormous amounts of atoms and molecules. And then you have Boltzmann's constant, which is the bridge that connects temperature to thermal energy. So this is where the new SI just completely changes the game. See, before, a number like Avogadro's was physically tied to something real, like how many atoms are in 12 grams of carbon-12. Well, not anymore. Now, these constants are just defined. They're perfect, unchanging numbers. They've basically been set free to become pure scale factors. And it's this freedom that lets us give them a brand new and honestly a much more elegant meaning. So let's start with Avogadro's number. I mean, how do you give a real, tangible meaning to a pure number that's just for counting? Well, the answer, surprisingly, has to do with perfect imaginary crystals. So you have to ask, right? If Avogadro's number is now just this perfect, defined number and it's totally disconnected from its old anchor, what does it even represent? What is it? The best way to think about it now is as a pure scale factor. Researchers Frondorf and Lipp put it perfectly. They say it's the bridge that connects the incredibly tiny atomic world to our everyday macroscopic world, the one we can actually see and touch. So how do you make this abstract idea feel real again? Well, the proposed solution is just beautiful in its simplicity. We decide to anchor it to a physical object, a perfect, theoretically buildable object where you could literally count every single atom. And the object they proposed? It's a graphite hex prism. Now, why graphite? Well, because it's super stable, and its structure is perfectly regular, like a tiny, flawless honeycomb. The idea is to define Avogadro's number based on a perfect crystal that has exactly 51,150,060 carbon atoms along each of its sides. It becomes this flawless, tangible, and replicable standard. And just like that, this unbelievably huge number is no longer just some abstract thing floating around in textbooks. It becomes something real. The exact number of atoms in that perfect, imaginable crystal. It finally has a physical home. Okay, so that's how we can bring some clarity to counting atoms. But our second constant, Boltzmann's, is hiding an even deeper secret. Turns out, it's not just about energy. It's about the fundamental currency of information itself. This is where things get really, really interesting.
In high school, we all learned that Boltzmann's constant, Kb, is just a simple conversion factor. It turns temperature in Kelvin into energy in joules. Easy enough, right? But that is not the whole story. Its real identity is so much deeper. It is the fundamental link between energy and information. And to really get that, we have to uncover its own hidden unit, a thing called the gnat.
To see this connection, let's walk through a classic thought experiment called the Szilard engine. Imagine a box with one single atom bouncing around inside. There's a divider in the middle, and we have no idea which side the atom is on, okay? Now we slowly push a piston in, squishing this one-atom gas into one half of the box. Doing that costs us energy, a very specific amount of work. But think about what we get for that price. By forcing the atom into one side, we now know where it is. We've gained information. And here's the incredible part. The energy we spent is the exact physical cost of gaining that one bit of information. Energy was literally turned into knowledge.
And this finally reveals that hidden unit we were looking for, the gnat. A gnat is just a unit of information that's based on the natural logarithm. So Boltzmann's constant isn't just joules per Kelvin, no. Its true identity is joules per Kelvin per gnat. It is the fundamental energy cost of information. It tells us the absolute minimum energy required to gain one gnat of knowledge about our universe. How cool is that?
So you see, by anchoring Avogadro's number to a perfect crystal, and by revealing the hidden gnat inside Boltzmann's constant, we can finally unhide this secret language. And when we do that, we start to build a much more explicit, a much more intuitive future for physics. So why go through all this trouble? Well, the payoff is actually huge. Of course, it cuts down on confusion, but more importantly, it uncovers these profound truths, like that deep, deep connection between heat and information. It lets us create elegant new standards, and it just makes the fundamental rules of our universe more transparent and accessible for everyone.
You know, in the end, the language we use to talk about the universe literally shapes how we understand it. Redefining these constants isn't just some boring scientific housekeeping. It's a real step toward a deeper, more honest picture of reality, which, of course, leaves us with one last fascinating question to chew on. What other profound secrets are out there, hiding in plain sight, just waiting for us to finally find the right words to finally see them?